Go over this example of static rotational equilibrium. This says that there's a 15 Newton force that's applied at an angle of 30 degrees at a distance 0.6 meters from the midpoint of this plank. The plank is 23 kilograms and 4.4 meters long. The fulcrum is placed directly below the midpoint of the plank. We want to figure out what the magnitude of the plank is and at what distance from the middle of the plank on the other side should a 1.1 kilogram mass be hung so that the mass maintains equilibrium. So what we're going to do is we're going to use a second law toolkit, both in the linear and rotational directions, and we're going to use it for static equilibrium. First, we're going to determine the accelerated system. In this case, it's the rod, that solid object there, the rod. The second step is to determine our coordinate system, where to the right is positive and counterclockwise is positive. Then we're going to draw the force diagram with motion map. So our motion map looks like this. Since the object isn't moving, we have zero linear and rotational velocity, zero linear acceleration, and zero rotational acceleration. Now, let's look at our forces. Let's start with the vertical forces. We've got a normal force up, a force due to gravity from the plank down, and a force of gravity down somewhere over here on this side of the plank from the hanging mass. H stands for hanging. Now, I'm going to explain why there's this horizontal component of the normal force as well. And I'll do that in a second. The applied force goes at an angle there, and we're told that it's 15 newtons. That angle's 30 degrees. Now, I said I would explain this horizontal normal force. This horizontal normal force is there because it's got to balance out this component, this horizontal component of the applied force. So if there was no applied force horizontally, this system would move to the left. And if there was no if there was no normal force horizontally there, this FAX would cause it to accelerate to the right. So those two have to balance each other out. Notice that they're obviously not to scale. They're supposed to be the FAX and FNX should be the same size if they're drawn to scale. All right. Now we want to explicitly write out Newton's second law in the linear and in the horizontal. So there they are. Again, because this is static equilibrium and nothing's moving, but the sum of the forces equals zero, the sum of the torques equals zero. Then we want to write the filled-in second law equations for each of them. In the vertical, we've got this Fny, okay, this Fgp, downward, the force due to gravity of the plank, Fay, this vertical component downward of the applied force, and the weight or the force due to gravity of the hanging mass. Those are going to add up to zero. Likewise, horizontally, we said this Fnx and this Fax have to balance each other out and add up to zero. The torques have to add up to zero as well. So anything that can make this thing spin, we're going to observe it and see whether or not it provides a non-zero torque. So we're going to look at this force Fay. Does it produce a torque Ay? We're going to look at Fny to see if it produces a torque Ny. And so the same with the force due to gravity of the plank. We'll see if that produces a torque and whether the hanging mass produces a torque. Okay, so let's see what calculations we can calculate at this point. So FGH, the hanging mass, we're told that it's a 1.1 kilogram hanging mass. So that's our usual equation for figuring out the weight or the force due to gravity is of an object. It's 10.8 newtons. I haven't included any signs yet. Fay, we can calculate that it is the perpendicular component of this force, and it's 7.5 newtons. If we look closer at the torques that we were talking about, the first, well, let's do that. The first torque, torque Ay, comes from the force Ay, which is applied at that location. Okay, I know it was drawn here before, but that was to show how we calculate out FAY. Now I'm moving it over to here so we can see where it's actually being applied. It's the same force in the vertical. So we figure out that it's 7.5 newtons. We did that just a second ago. We're going to multiply times this distance RAY, which is from there to there, 0.6 meters. Now the normal force in the vertical, notice, it is applied right there at the axis of rotation. So it has, there's no R to it. It's a distance 0 from the axis of rotation. So that's going to become 0. The same thing with the force due to gravity of the plank. It's also a distance R from the axis of rotation. So it's also going to be 0. Our hanging mass, we figured out earlier, is going to be 10.8 newtons, and it's going to be over here, and it's going to cause us to go clockwise, so that's why we have a negative sign here, and we're going to multiply that times R, which is some distance from here to here, and we'll call that RGH. If I solve this equation, I eventually end up with this expression here, and I could solve for R as RGH, so 0.412 meters. So what we calculated was the torque of this applied force, and we also calculated how far FGH, the hanging mass, is from the axis of rotation.